We are very fortunate to have our Dr. Brian Dixon with us this morning. And if you don't know who Dr. Brian Dixon is, he's relatively new to LifeVantage. He's been here, well, time certainly does fly. So it's been longer than it seems.
Yeah, almost
But
9 months. You can believe
yeah,
that.
so I mean, it is flying by, and we've certainly had some adventures while we're here. But Dr. Dixon comes to us with an incredible background in biochemistry and biology. And the great thing about what Dr. Dixon brings to LifeVantage is that he's the scientist, so you don't have to be. He breaks down some really complicated topics and some really in-depth knowledge on how things work at the DNA level. And then we make him available through formats like this one so that you don't have to go and learn all of that. So without further ado, let me kick it over to our Senior VP of Research and Development, Dr. Brian Dixon.
Yeah, thanks so much, Dave. And it's so good to see everybody. The numbers are amazing yet again. I'd also like to echo Dave's sentiments and just wish everybody a very happy Easter weekend. Hope you're doing something fun, hiding Easter eggs for the kiddos. So normally you've heard me talk, and we've talked about nutrigenomics before, but I'm going to take just a little bit of a different angle than maybe we've talked about nutrigenomics in the past. And before I dive into the presentation, I might just kind of maybe plug a new social media platform that I've been working with the social media team on. So I'm closing down my personal page and shifting everything over to just at Dr. Brian Dixon. So I'll be working closely with the LifeVantage social media team. And it's our promise that we're going to keep sharing all sorts of different health content. And so we'd love to just gather as much of a like-minded community that's centered around health and wellness and trying to live their best lives, especially through nutrition and a healthy lifestyle. So if you would, just kind of like and follow me over there at Dr. Brian Dixon, and we'll continue to roll out all sorts of great content. So like I said, I'm going to take a little bit of a different approach to nutrigenomics. Normally when we talk about nutrigenomics, we talk about nutrition working through cell signaling to turn on genes. And if you didn't see the first presentation where we were talking about all that kind of biochemistry and molecular biology that's happening, I'd encourage you to go back and listen to the first one of these success mastery trainings and kind of get brought up to speed. But what I'm going to focus on more today isn't so much at the genetic level, but how we can optimize our cellular biochemistry. So this might get a little bit scientific. And like Dave said, if this isn't something you're into, if you don't love science as much as I do and biochemistry as much as I do, I know Rebecca loves this stuff. She's over there grinning ear to ear. But if you don't love it, just try to take some key takeaways. But I want to show you another example of just how powerful nutrigenomics can be to help optimize our cellular function. So on the screen right now is a map of all of the biochemical pathways that are going on inside of this cell, literally every millisecond of every day. So I promise we'll walk through this really slowly. I'm kidding. But I just want you to grasp how complex it is. And then it's funny thinking back to my graduate study days, I actually had to memorize all of these pathways. And this is one reason why I have such massive respect for especially pharmacists. Pharmacists have to know this stuff inside and out, and then how everything we're putting into our bodies can interact with all of these different biochemical pathways. But I have some hard scientific proof that at one point, I actually had all of these pathways memorized. Are you ready? Hey, how about that, nerd? I think that's about my second year in graduate school, just grinning ear to ear. Yeah, I had my ear pierced. I think that's a requisite to live in Oregon. You have to have at least one piercing. But look at my pins in my lab coat pocket. I've got my Linus Pauling Institute lapel pin on. I'm just nerding it out to the max. But I want to come back to this biochemical pathways and then what we can do to optimize it. And so to kind of walk you through how nutrigenomics can interact with this biochemistry and really optimize it, I want to use a specific pathway as a surrogate or an analogy to walk us through that. And so that pathway is the glutathione pathway. Now, if you haven't heard of glutathione, don't worry about it. That makes you normal. It's probably the most important molecule in our body that nobody has ever heard of. So let's talk a little bit about glutathione and what it is. So glutathione, besides water, is the most abundant single molecule in our bodies. So just right there alone, because it's so abundant, it must be doing something important. So just some of the key functions that glutathione has inside of our bodies is, one, it determines our redox status. And apologies, I know that's a little bit of scientific jargon, but what redox status is really analogous to, let's say, pH or body temperature. So we know that our bodies like to regulate pH, right, our body temperature within very, very tight ranges. I mean, if we fall just a few degrees either above or below our optimal body temperature, it has severe consequences to the cell. Well, the same is true with redox status. And what redox status is determining whether or not the cell is more reducing or more oxidizing. So we need to stay in this sweet spot of reduced to oxidized to make sure that all this biochemistry can happen. And so, if you want to think about antioxidant protection, right, and we've got oxidants on the other side, so it's maintaining this balance. Glutathione is essential for detoxification. So just like antibodies are working in our immune system to basically tag foreign invaders inside of our bodies so that our immune system can work on them and get them out of our bodies, glutathione works a lot of that same way. It will actually attach to different toxins and then facilitates their removal from the bodies. And then maybe glutathione's most famous role is one of an antioxidant. Now, glutathione's an interesting molecule because it's actually a protein. It's a protein that's made by our bodies, okay? So you cannot take glutathione orally and, forgive me, but, all this garbage about, glutathione supplements and glutathione phytosome, it doesn't work. You cannot take oral glutathione, get it into your bodies, and have your body appreciably increase glutathione levels. You have to support your body's natural ability to make glutathione. But what's so interesting about glutathione is that even though it's a protein, it's made in a different way than most proteins inside of our cell are made. So it's made by a couple of different enzymes. So most proteins inside of our cell, and this is going back to some basic high school or college chemistry, biochemistry, molecular biology, but most proteins inside of our bodies are made by these things called ribosomes, if you'll remember. And ribosomes, in my mind, work a lot like a typewriter. So they're really reading the genetic code. And the way that they do this is there's a little messenger molecule that kind of transcribes the message that's inside of our DNA and our genes. And then it goes outside of the nucleus and it attaches to the ribosome. And that little messenger molecule is called mRNA or messenger RNA. And then the ribosomes, just like a typewriter, will start to read these different pairs, or actually triplet pairs, and each one of those triplet pairs codes for a specific amino acid. So as this ribosome typewriter is working its way down this message, it's signaling to the ribosome exactly what amino acid to attach next in that chain of amino acids that eventually becomes the protein. But that's not how glutathione is working. So again, I know this is a little bit complex, but what I want to illustrate is that glutathione is a protein that's made by two enzymes, not on ribosomes. But what's so interesting about these different enzymes is that they can actually be activated by the protein NRF2. Now, if you see me talk, you know that I love molecular structures. I promise we're not going too far into this. To me, they're super interesting because you can look at these structures and get a pretty good idea just by looking at them, even if you don't know how they're working. So this is the molecular structure of glutathione. It's an incredibly small protein that's made up of just 3 different amino acids. They're glutamate, cysteine, and glycine. Okay, so that's what makes it a protein. So as I mentioned, glutathione's made by 2 different enzymes, and we'll just call them enzyme 1 and enzyme 2. Now, they do have names, very complicated names, gamma-glutamyl cystenyl ligase, and then glutathione synthase or synthetase. But again, I want you just to think about this as enzyme 1 and enzyme 2, okay? So remember, I'm using glutathione as a surrogate for how we can utilize nutrigenomics, not just for glutathione production, but also for many pathways inside of our total metabolome, they call it. So how can we think about how this cell is working and all of that machinery and biochemistry that's going on? Another simple analogy that I like is one of a factory. So for these biochemical pathways, what we're really doing is putting raw materials in, and then we get our widgets out. But if we transition that into how the cell is working, we get these molecular building blocks or raw materials, either from our diet or from the metabolism. They go through the cellular machinery, and then we get these active molecules out. Okay, so think of a factory in your mind's eye. So all of these biochemical pathways are working exactly like an assembly line inside of a factory. So on the screen, we've got about 6 workers there that are assembling these widgets. Raw materials in, they're going through these series of steps, and then we get our widgets out. But if we label how efficient each one of these workers are, so the first 3, let's call those fast workers, and then number 4 there, let's call him that guy or gal that you don't like working with so much at work, the one that's kind of holding up everybody else's work. We'll call him the slow worker, and then maybe we have 2 fast workers after him. But what's going to happen to the efficiency of that assembly line with that slow worker kind of right there in the middle? Well, what's going to happen is because there's that fast worker right next to him and that slow worker on the other side, these widgets are going to back up at that last fast worker because the slow worker can't work fast enough to process the materials that he's making. And then the other consequence that that slow worker will have is, even though we have some great workers at the end of the assembly line, they are limited in how quickly they can work because of the slow worker not giving them as many widgets as they can handle, okay? So enzymes in these biochemical pathways can be thought about these machines or these workers inside of the cell. And so if we come back to this glutathione synthesizing pathway, what if we change this into just a simple cartoon and we just call them enzyme 1 and enzyme 2, okay? So again, it's working the same way. We have raw materials coming in. So in this case, it's going to be those amino acids that are required for glutathione production. Then we have the first enzyme that brings the first 2 amino acids together, and then that last enzyme that puts on the final amino acid, and we get active glutathione to come out. It turns out that that first enzyme in this glutathione synthesizing machinery is actually the slow enzyme, okay? So the first enzyme in the step to make glutathione is actually holding up the entire process. Enzyme 2 could actually process more of the substrate, this intermediate, than enzyme 1 can. So enzyme 1 is holding everything up, and it's what we call the choke point in this biochemical or glutathione synthesizing pathway. A simple way to think about these choke points is like one of a funnel. So if I have a funnel and then I'm pouring water into the top of this funnel, water can only move through that funnel as fast as its narrowest point in that funnel, okay? And it doesn't matter how much more water I pour in to that funnel, it's only going to go through that funnel as quickly as its narrowest point. So raw materials in, right? You can put as many of them in as you want, but the widgets you're going to get out are dictated and mandated by that choke point in that funnel. And the same exact thing is working inside of the cell and these different biochemical reactions. So what could we do if we actually wanted to maybe increase the efficiency of these different biochemical pathways? Well, it turns out that there's a couple of different approaches that we can take. So the first approach we can take is that we can add more raw materials into the system. But if this approach, I should say, only works if the substrate or those building blocks are limiting. Okay? Remember, it's like pouring water into a funnel. So if we have enough of these molecular building blocks or substrates or these amino acids, it's not going to help speed up the reaction. Okay? So then what would be the second approach? So think about that assembly line in the factory, right? That assembly line's only working as fast as its slowest worker. But what if we built a second assembly line inside of that factory? So this is exactly the second approach that we can take. So in this example where we went from one assembly line or enzymatic pathway to two pathways, we've literally doubled the capacity of this biochemical pathway or this little assembly line, right? If we add two more in there, we've doubled it again. So what we really want to be doing when we have these limiting enzymes in these biochemical pathways is we want to look for strategies where we can increase the number of enzymes, effectively building another assembly line inside of the cell to increase the overall efficiency, and in this case, the production of glutathione. And so then obviously the best approach is going to be making sure we have enough of those substrates. So in the case of glutathione, to get those amino acids, it's very easy to do by just eating a healthy diet. And then what we want to do is start to employ strategies where we can increase the number of enzymes inside of these biochemical pathways. So we want to hit it from both sides. And so what we're trying to do is increase the amount of glutathione. And so we can do this by increasing the enzymes. And if you remember me telling you early on in the pathway, it turns out these two enzymes are under the regulation of NRF2. So another example of why Protandim NRF2 Synergizer is so powerful. It's not just increasing these detoxification enzymes, it's not just increasing these antioxidant enzymes, but it's also increasing enzymes that are very important in a number of biochemical pathways, including glutathione synthesis. But we can also talk about Protandim NRF1 Synergizer and helping increase these various pathways that are related to mitochondrial health and turnover of these mitochondria. And then we can also talk about Protandim NAD Synergizer, increasing the enzymes responsible for NAD biosynthesis. So we're trying to increase the efficiency or efficacy of these different biochemical pathways. And then again, this is exactly why it's so important and why we say that we need to flip these switches to feel better and do more. So not only are we working on a genetic level, but we're also helping our full cellular biochemistry function more optimally. And you know, a question I get probably more than anything out there is, okay, if I just have to take one product, what would it be? And for me, quite frankly, it's impossible to answer. So if you can picture that big metabolism picture I just put up earlier in the presentation, it would only be like trying to optimize one small corner of that. So what we really want to be doing is trying to optimize all of these genetic switches. We want to try to be optimizing as many biochemical pathways as we can, and why I just always have to recommend that you turn to all three of the Protandim family of products, and especially the Tri-Synergizer. And so with that, I hope that gives you just a little bit more strength, a little bit more background of the power of nutrigenomics, and just another reason why it's so important to help us live our best lives possible. So thank you, everybody, for tuning in this morning and this afternoon, wherever you might be.